So we'll revisit a few concepts that we saw in this section. First of all, let's talk a little bit about Georg Cantor. He was a German mathematician from the 19th century. That was a century where there has been an enormous number of great German mathematicians. And he was the founder of set theory. And he discovered that there are different sizes of infinity. In fact, there are infinitely many different sizes of infinity. And back in the days, it really shocked the mathematic world, and many people attacked him. Many people thought he was crazy. And the reason for that is that his new theories brought a lot of contradictions with them. So people refused to accept them. And it took many years until the early 20th century until mathematicians started to accept what Cantor had discovered. Cantor suffered from depression and he stopped working on mathematics later on and died in a sanatorium. So infinity, we used to think there was just one, and Cantor showed that there were many, many, many. So we'll talk a little bit about that. First, let's wonder, where does this sign for infinity come from? It is not, it didn't come from Cantor. It was chosen in the 17th century by a mathematician called Wallis. Nobody's quite sure where it comes from. Some people assume it's like an M, a stylized M, and M would be the number in the Roman numeral system, which is the largest number there is. It's 1000. Some people think it comes from the letter omega in the Greek alphabet. Omega is the last letter in that alphabet. Other people think it's connected to Vishnu, the Hindu god. So Cantor, when he discovered that there were different sizes of infinity, thought that it was such a new theory that it deserved a new alphabet. We use a lot of Latin letters in math. We use Greek letters as well. He introduced the Hebrew alphabet, and this is an Aleph. So it's the first letter of the Hebrew alphabet to define the size of infinities. So Aleph naught is the smallest infinity. It's the natural numbers. It's any set that you can count. Aleph 1 is bigger than that. It's, for example, the number of real numbers. And Aleph 2 is even bigger than that. For example, it's the number of continuous functions between 0 and between the origin and the point 1, 0. By the way, since we're talking about that, one thing that is still unknown in mathematics is whether there are sizes of infinity between Aleph naught and Aleph 1. So for the moment, nobody has discovered a size of infinity which is between the natural number and the real numbers. It's an open question in mathematics today. So Aleph naught, any set that we can count, even though it's infinity, we can arrange them in order. Aleph 1, the number of points on a line. Aleph 2, the number of continuous functions between 2 points. So let's be clear. When we say countable sets, it means we can name the first element and the second element and the third element and the fourth element and so on. So for example, what we saw in this section is that the integers are a countable set, and if you start at 0 and you would just go to the right, that would not be the proper way of showing it. On the other hand, if you jump back and forth between the positive and the negative numbers from 0 to 1 to -1 to +2 to -2 and so on, then you order them in a way that you can say, this is the first element of my list, this is the second, this is the third, this is the fourth, this is the fifth, and so on. So what we'll see in the next section, and it's a very important theorem, is that even the rational numbers is a countable set. So when you think about it, all the rational numbers, 2 over 3, 5 over 3, 4 over 7, 8 over 5, 12 over 17, it seems like there's going to be a lot more than the natural numbers. Well, Cantor found a great way to organize them in a way that you can list them. So what I'm showing here is not absolutely correct, because in my list here you can see that the same number appears several times. For example, at the bottom left, 1 over 1 is really the same number as 2 over 2, 3 over 3, 4 over 4, 5 over 5, 6 over 6. Likewise, the fraction 1 over 2 is represented 3 times just in this grid, because it's equal to 2 over 4 and 3 over 6. But we could remove these repetitions, and what I want to show here as an introduction is just the basic idea behind the proof that rational numbers are a countable set. So what you do is you start at 1 over 1, then you go to 1 over 2, and then you turn to 2 over 1, which basically is the number 2, then you go to the number 3, and then you go down the diagonal again. This one we should technically skip, because we've found it already, to 1 over 3, to 1 over 4, and then up along the diagonal again, and so on. So by visiting all the rational numbers like that, we can start naming them, the first element, the second element, the third element, and so on. So it's a countable set, etc. So Aleph1 refers to a greater infinity. It's an infinity that we cannot list. We can't say this is the first element, this is the second element, etc. And to prove it, Cantor actually chose an example and said, let's pretend that we can. And when we do that, he said, okay, let's just take a random example. 0.43523456566, 0.26676. These would be my first 2 numbers in my infinitely long list. And what Cantor did is he built a number that wasn't in the list. So it's a clever trick. You take the first number after the decimal point, and in your own number that you're building, you just make sure you choose another one. So instead of 0.4, I'm going to choose 0.3. And then for the second number, you choose the second decimal after the decimal point, and you choose another decimal for that place. So instead of 6, we choose 4. Now we know our number is definitely different from the first number, it's definitely different from the second number, and because we choose a third decimal point that's not 7, we know it's going to be different from the third in our list, it's different from the fourth, and basically it's different from every number in the list. So that shows that our list wasn't complete because we're building a number that wasn't there. So here's a number 0.34138455532, etc., etc. That was not on the original list. Therefore, it's not possible to make a list. It's not possible to count the real numbers. So here's another fact that Cantor proved, and that's that the segment from 0 to 1 is equinumerous to a longer segment from 0 to 4 maybe, and the way to do that is to pair each point on the lines. Now this is a little bit different from the notes we saw. Instead of having this segment 0, 1 vertically, we just curve it in a way that we can now connect the points like this. But it's of course, similar. So that way we see that each point on the segment 0, 1 is paired with one point exactly on the segment 0, 4, and vice versa. Each point on the segment 0, 4 is connected to a point on the segment 0, 1.